Howdy AP PreCal, it is Miss Kosh. I'm going to try that last semi-log plot problem again, okay? I'm definitely still learning this stuff. I was talking with a student, shout out to Bragov, and as we were talking through things, all of a sudden I was like, okay, this is making more sense to me. Let me see if I can improve my video. So here goes nothing. I have a table, I think it's the same table from the last video. I can come over here in Desmos and hit that little magnifying glass and get a better view of things. The normal world that we live in is not very helpful, so we're going to change this to the y-axis being logarithmic, so we can have a semi-log plot. So here are our points. And now we were coming up with, I didn't do a great job of explaining why the equation was what it was and all that kind of stuff. So I think I can do a better job now. So first of all, this appears to be a line, okay, and so in the semi-log world, it looks like a line, and if you know, a line would have y would equal mx plus b, right? And so the m is the slope, or what have we been studying all year long, the average rate of change. So what we're going to do is we're going to find the average rate of change, and what we'll say here, our average rate of change will be equal to, well, keep in mind, the points, we would have so say I'm going to use 1 and 2, so it's 2 minus 1 in the denominator. That first value, though, in the y values are not just the values off of this table, it's log of that value. So we'd have log of 80 minus log of 20 all over 2 minus 1. Okay, so I said 20 and wrote 2. Okay, so 2 minus 1 is 1. We don't need to divide by 1. And so this becomes log of 80 over 20. Well, you'll know that that equals log of 4. Okay, so this is our average rate of change. This is our m value. And then we can go about finding our y-intercept. We know that we have the point, well, one of the points, we could also say, well, let's use our value. We have the point 1 comma, this would be log of 20, would be the y value in our linear world. And so if I plug in that point, I can solve for b. So I can say my y value is log of 20 is equal to my m value, my slope is this. I'm going to go ahead and put this in parentheses so that we know, or I could have written it as, well, this is, Notability looks funny right now. I could write it this way. Okay, those are equivalent, but it is not equivalent to say this, log of 4x, because we assume that the 4 is multiplying by x, and then we're taking the log of it. So don't write that, but if you want to put it at the back like I did on that first line, then you'd have to put parentheses around the log. Okay, plus we have plus b on both of these, so plus b. I just wanted to make my statement true. So now, oh, what did I forget? I forgot to plug in the x value. So the x value, the eraser goes away. I always forget that. Okay, so the x value was 1, or you could write it there. And so what I'm doing to solve for b, b would be equal to log of 20 minus log of 4. So how do I squish subtraction? I squish it with division. And so my b value is equal to log of, well, 20 over 4. Hopefully you know that that's 5. So what happens here is the y value, it's not just going to be y equals these sorts of things. It ends up being log of y is equal to m, what's the m value? Log of 4 times x plus, what's the b value? Log of 5. Okay, so when I come over here, I can say function, let me find it, log of y is equal to log of 4, close the parentheses, then multiply it times x. Notice already it's parallel to what came before, what we need to change. And in my previous video, we talked about that. Sort of. Have I passed it? Yes. Oh, goodness. Okay, there it is, log of 5, and close parentheses, and notice that matches those points perfectly. Okay, so now let's think about this in the world of exponential functions. We know that if we have a line in a semilog plot, that relates back to an exponential function. Well, what's our initial, if this is my exponential form, then I have an initial amount is my A, and my growth factor, or decay factor, but in this case it's growing, is B. Okay, so what's happening here? Well, let's see. If I say the initial amount would correspond to B in my linear world, right? Because B is the y-intercept. It's what happens at when x equals 0. So let's plug in. But we no longer want to have the log. Oh, actually, no. I found a better way to do this. Okay, sorry. You can do what I was trying to do, but this is better. Watch this. If I rewrite this, I have log of y is equal to log of, well, let me write it this way. Somebody is loud in the hallway, and let's do it this way. But it is after school, and my mother used to say, I'm done being a mom when it was late at night, and now I'm done being a teacher. I don't want to deal with them. Okay, I'm so sorry. So writing it this way, we can see that x becomes the exponent. Okay, and now how do we squish addition together? We squish addition together with multiplication. And so I have log of y is equal to log of 5 times 4 to the x. Well, notice if I have log of something equals log of something, then the somethings have to be equal. And so I have y is equal to 5 times 4 to the x. Notice if I come over here and type in y equals 5 times 4 to the x, notice that green right there is exactly the same line. Hallelujah. Okay, and look, if I come back here and change this back to my linear world, both of these lines, if I turn them off and on, why isn't that working? Okay, I hit the wrong thing. It's the same curve. Okay, the last little bit I wanted to point out was if this is my initial amount, well then this is also my initial amount. If this is is involved in my rate of change, then this would be involved in my proportional rate of change. You see how all these things are connected? I'm getting better at this. Hopefully that was helpful. Like, subscribe, comment, and go practice, and let me know how I can help you. All right, good luck.